Imagine just beyond the orbit of Mars a celestial body glows with a symmetry so precise it defies every known law of cometary physics. Not almost perfect, not close enough. A staggering 99.9999% symmetrical. This isn't how comets are supposed to look. They're cosmic cannonballs, chaotic, spitting ice and dust in messy, unpredictable bursts. Yet Comet C2023A3, now famously known as 3I Atlas, has chosen to be different. The images from November 10th presented a spectacle astronomers had genuinely never witnessed, a perfectly spherical tailless orb of light where a messy comet should have been. Tonight we delve into why this impossible object has some scientists whispering a single chilling word: engine. The implications are both breathtaking and terrifying. Just last year, on November 10th, 2023, an impossibility unveiled itself in the vast canvas of the night sky. Amateur astrophotographers, those diligent cosmic hunters across the northern hemisphere, meticulously pointed their telescopes towards a faint smudge in the constellation Pisces. Stacking 30-minute exposures, a common technique to pull faint details from the darkness, they were searching for the usual cosmic intricacies. What materialised on their screens, however, was not just another comet. It was something utterly unprecedented. Within hours, online forums buzzed with the strange new images. Long-time observers who had tracked 3I Atlas for months found their expectations shattered. Instead of the familiar chaotic tail, the signature spray of dust and gas that defines every comet ever studied, they saw a pristine sphere, a glowing, intensely symmetric core. It resembled less a dirty cosmic snowball and more a miniature star enveloped in some kind of exotic plasma. Analysts measured its symmetry at an astonishing 99.9999%. Such precision, such flawless geometry is typically reserved for objects meticulously crafted, not bodies that have drifted chaotically through interstellar space for eons. To truly grasp the magnitude of this anomaly, let's revisit what a typical comet is. For centuries, these dirty snowballs, frozen remnants from the solar system's birth primarily from the Kuiper Belt and Oort cloud, have appeared as majestic yet fundamentally chaotic celestial wanderers. As they plunge into the inner solar system, solar radiation unevenly heats their icy nuclei. This causes ice to sublimate, erupting in powerful, randomly directed jets of gas and dust from active regions. These jets, dictated by the comet's irregular shape, its tumbling rotation, and varied surface composition, create those spectacular million-kilometre-long tails. Chaos is their defining characteristic, a testament to their primordial untamed nature. But Comet 3I Atlas, this interstellar drifter, defied every one of these established norms. The November 10th images showed no such chaos. Instead, a perfectly circular, intensely luminous core pulsed with a symmetric glow. No streaming tail, no discernible jets firing off-kilter. It was an eerily perfect sphere of light, as if a star had been meticulously miniaturized to a mere few kilometers across. Many observers grappling with this visual paradox have begun abandoning the term comet, altogether opting instead for plasma star. And the description feels eerily apt. The quality of its light radiating uniformly in all directions doesn't align with the expected outputs of traditional outgassing. It perfectly evokes plasma, that fourth state of matter where atoms are stripped of electrons glowing intensely with electromagnetic energy. Yet natural comets lack the necessary energy budget to generate such a brilliant symmetric plasma core. While solar heating can induce some plasma in a comet's coma, it's never anything approaching this level of organised radiance. This leaves us with a profound mystery diverging down two drastically different paths. One path suggests this stunning symmetry is merely an artifact, an optical illusion, or a trick of image processing deceiving us into perceiving order within what is fundamentally a chaotic cometary display. If this is the case, we could comfortably return to our conventional understanding of comets. However, the second more unsettling path posits that the symmetry is physical. It is real. If so, then we face a far greater challenge explaining how a natural object, A mere conglomeration of ice and rock could possibly achieve such geometric perfection. The artifact hypothesis initially seemed plausible. 30-minute exposures typical for astrophotography involve stacking hundreds of individual frames. This process of alignment and light combination could in theory smooth out irregularities. Perhaps the comet's rotation during exposure blurred its jets into a uniform symmetric halo. Or maybe our viewing angle conveniently obscured the tail behind a bright central core. These are indeed the first considerations any professional astronomer would raise urging caution against immediate exotic conclusions, a cornerstone of the scientific method demanding extraordinary evidence for extraordinary claims. Yet the astrophotographers capturing these images are not careless novices. They're often highly skilled practitioners, intimately familiar with their equipment and processing software. Crucially, many reported that the symmetry was evident even in the raw data prior to stacking or intensive post-processing. Furthermore, independent observations from different telescopes located in disparate parts of the world consistently reported the same identical geometric properties. This widespread corroboration significantly weakens the optical artifact explanation. When multiple unconnected observers using varied equipment see the same impossible perfection, the physical reality of the phenomenon becomes harder to deny. This brings us squarely to the physical explanations, and this is where the narrative truly veers into the genuinely strange. If the observed symmetry is indeed a physical reality, meaning this object has truly reorganized into a perfect sphere of glowing material, then a powerful mechanism must be at play. The first natural candidate is rapid rotation. If an object spins fast enough, centrifugal force can distribute any ejected material evenly, creating that illusion of a symmetric glow. For a nucleus several kilometers across to blur into a perfect sphere over a 30-minute exposure, its rotation period would need to be incredibly short, perhaps just minutes or even faster. This implies surface velocities approaching hundreds of meters per second rates that push the very limits of what an icy body can sustain before it rips itself apart. While comets can spin rapidly, usually over millennia due to continuous outgassing, torques, 3I Atlas is an interstellar visitor making its first and only pass through our solar system. There's no known natural mechanism for it to have spun up to such extreme speeds in the short time frame of its solar system encounter, or even to have acquired such a spin during its formation or journey across the galaxy without being torn apart. This leads us to a far more provocative, albeit quietly whispered alternative, the possibility that this symmetry isn't natural at all. What if we are observing something designed? It's in these hushed conversations, sometimes surfacing in preprint papers, couched in cautious, probabilistic language, that the word engine emerges. The phrase propulsive origin is not unheard of. Consider an interstellar spacecraft if it were engineered to mimic a comet, yet required a symmetric thrust system for precise course corrections. Its drive plume or a controlled plasma field might very well present as an almost natural-looking phenomenon from a distance. Up close, however, such a system would reveal a geometric perfection that nature simply doesn't produce. This line of reasoning, I know, represents a monumental leap. It's the kind of speculation that traditionally invites ridicule in academic circles, and skepticism is a scientist's most vital tool. Extraordinary claims, after all, demand extraordinary evidence. Currently, we possess only compelling images showcasing unexpected symmetry. But this initial anomaly, striking as it is merely the tip of the iceberg. As we probe deeper into 3I Atlas's actual behaviour, its precise motion tracking, spectroscopic data, and acceleration measurements, a cascade of further observations emerge, each individually puzzling, but collectively forming a pattern that challenges our most fundamental assumptions about interstellar objects. Whether 3I Atlas proves to be an exotic natural phenomenon or something else entirely, it is already rewriting the cosmic rulebook. The fundamental question might no longer be whether we're seeing a comet or a spacecraft, but rather if we can even tell the difference anymore. When Comet 3I Atlas finally re-emerged from behind the Sun in early November 2023, astronomers worldwide held their breath. teams like those at the Arnaves Observatory in Spain had diligently tracked the object for months, meticulously predicting its trajectory as it navigated the inner solar system. Solar conjunction, the period when an object passes directly behind our star from Earth's perspective, inevitably creates an observational blackout, sometimes lasting weeks or months. But astronomers know where to point their instruments once the object clears the solar glare. The first post-conjunction images from the Naves team in early November immediately flagged a problem. The tail, where was the tail? Every comet, even faint ones, is expected to develop some form of tail as it nears the Sun, driven by the solar wind and radiation pressure. 3i Atlas crucially had shown clear cometary activity in previous observations from September and October, complete with a diffuse coma and even a faint tail. The scientific consensus was that this activity should only intensify as 3i Atlas approached perihelion, its closest point to the Sun. Instead, the November 10th images showed an object utterly devoid of any obvious tail structure, replaced by that bright, centrally condensed, roughly symmetric coma. Nothing streamed away. This peculiar observation immediately caught the attention of Avi Loeb, the Harvard astrophysicist, who has become a deeply polarizing figure in the scientific community due to his controversial willingness to explore exotic, even artificial explanations for interstellar objects. Loeb had been tracking 3i Atlas closely, undoubtedly reminded of Oumuamua, the first confirmed interstellar visitor in 2017, which also exhibited anomalous non-gravitational acceleration. Loeb's bold hypothesis, then, that Oumuamua's behaviour might be consistent with an artificial origin, had triggered a firestorm of professional pushback and debate. Now here was another interstellar object behaving oddly, and Loeb was meticulously taking notes. But Loeb didn't just notice the missing tail. His analysis of months of precise trajectory data compiled from positional measurements across numerous observatories revealed something even more perplexing. 3i Atlas was accelerating, not merely moving along its predicted gravitational path, but displaying what astronomers term non-gravitational acceleration. This acceleration had two distinct components: a radial force pushing directly away from the Sun, which could be explained by typical cometary outgassing, creating a rocket-like thrust. However, there was also a transverse component, an acceleration perpendicular to the Sun line. This latter component is far more challenging to reconcile with simple conventional outgassing models. Non-gravitational acceleration in comets isn't inherently revolutionary. It's a well-documented phenomenon, albeit usually small, where a symmetrical gas jet subtly pushed the comet off its purely gravitational path. What was revolutionary, however, was the sheer magnitude of 3i Atlas's acceleration, and its staggering implications for mass loss. To understand this, let's briefly touch on the underlying physics. A comet accelerating due to outgassing is essentially a natural rocket. As material is ejected from its surface at high speeds, conservation of momentum dictates that the comet itself must gain velocity in the opposite direction. Newton's third law in action. The math is clear: the comet's mass multiplied by its acceleration equals the rate of mass ejection multiplied by the velocity of that ejected material. It's the same principle driving our spacecraft, just significantly less controlled and efficient. Loeb applied this principle to 3i Atlas, working backward from the measured acceleration. Assuming a typical outgassing velocity, a few hundred meters per second for sublimating volatiles like CO2 or water ice, he calculated the mass loss rate required to generate the observed thrust. The resulting figure was immense. At least 10% of the object's total mass would need to be ejected over the observation period. While comets do lose mass, this rate would produce a gargantuan cloud of debris. Gas and dust expanding at hundreds of meters per second would spread across millions of kilometers, creating a spectacle easily visible through telescopes. Yet in those November 10th images there was no obvious debris cloud, no discernible tail, no expanding shell of ejected material. The expected physical evidence of such prodigious outgassing was simply absent. Loeb pushed his calculations further. If this sustained acceleration truly resulted from outgassing, then the object's total mass, and thus its size, would have to be far greater than initially estimated, perhaps a nucleus larger than 10 kilometers across weighing billions of tons. A 10-kilometer nucleus losing 10% of its mass should create a truly spectacular, unmistakable cloud. We should be deluged with data on its tail structure, dust composition, and gas emission lines. Instead, we have images of a symmetric core with no clear tail. This is the heart of the 3i Atlas paradox. The trajectory data demands substantial mass loss, while the imaging data provides no obvious evidence of it. The expected debris cloud is missing the tail structure, conspicuously absent. Something in this scientific reasoning is fundamentally askew, but what remains elusive. Contributions from space-based observatories have further enriched the dataset. NASA's MAVEN spacecraft, typically dedicated to studying Mars's atmosphere, managed to capture observations of 3i Atlas during its inner solar system passage. Similarly, the Solar and Heliospheric Observatory SOHO, a constant sentinel monitoring the Sun, also detected the object in its wide-field cameras. These observations, while valuable, have not definitively resolved the paradox. They confirm the presence of some cometary coma around the nucleus, but critically nothing proportional to the prodigious mass loss implied by the momentum budget calculations. The missing evidence continues to haunt the data. Across the online astronomy community, a schism has formed. Dedicated Reddit threads for 3i Atlas have become intellectual battlegrounds between those convinced we're witnessing something genuinely anomalous and those who caution that we're likely observing conventional cometary behaviour from a disadvantageous viewing angle. Calls for increased observation time, more comprehensive data, and systematic monitoring campaigns resonate from one side. From the other, warnings against premature speculation proliferate, citing astronomy's long history of apparent anomalies, eventually yielding to mundane explanations once superior data emerges. Avi Loeb, true to form, has been characteristically outspoken in floating exotic possibilities. He posits that the missing tail could be resolved if the acceleration is not caused by outgassing at all. If an alternative mechanism is providing thrust, then the expected proportional mass loss and its associated debris cloud would simply not exist. This immediately raises the unsettling question, what else? What mechanism could propel an object weighing multiple kilometers without producing any visible exhaust? The realm of natural explanations quickly narrows, pushing us towards increasingly speculative scenarios. Professional astronomers, often distinct from Loeb's more provocative stance, typically advocate for extreme caution. They highlight the notoriously variable behaviour of comets, where outgassing can abruptly cease active regions, go dormant, or viewing geometry can mask tails behind a bright coma. Furthermore, image processing, while powerful, can sometimes inadvertently suppress faint, extended structures. All these remain legitimate possibilities that demand exhaustive investigation before extraordinary conclusions are drawn. Yet even the most circumspect scientists concede that 3i Atlas's observations are undeniably odd. This object is not behaving like a typical comet, and it warrants continued intense scrutiny. What we are witnessing is the raw scientific process unfolding in real time, its pace dramatically accelerated by social media and global public interest. Hypotheses are being generated and debated, data is being shared openly, and arguments rage in astronomy forums and Twitter threads with the same fervour typically reserved for peer-reviewed journal papers. Meanwhile, 3i Atlas continues its journey seemingly oblivious to the whirlwind of speculation it has ignited. The overarching question remains, do the November 10th images, those symmetric plasma star photographs, signify a genuine transformation in the object's behaviour, or did our observational capabilities simply catch up to its inherent strangeness? And if it did change, what triggered such a profound metamorphosis? Why would a comet shed its tail and reorganise into perfect symmetry precisely when passing through the inner solar system, at the very moment solar heating should be increasing its activity, not diminishing it? These questions, currently without answers, propel us toward the next critical layer of the mystery 3i Atlas's chemical composition. Every comet carries a unique chemical signature, a cosmic fingerprint etched into the light it reflects and emits. As sunlight strikes a comet's surface, Volatile ices sublimate, skipping the liquid phase entirely. These gases then fluoresce under solar ultraviolet radiation, emitting light at specific wavelengths that correspond to distinct molecules. A spectrograph, a powerful astronomical tool, can then read this light, deciphering the comet's composition and offering clues about its origins and formation history. For decades, we've built an extensive catalogue of normal solar system comet chemistry. 3I Atlas, by these established standards, is anything but normal. The James Webb Space Telescope, JWST, humanity's most advanced infrared observatory, was directed toward 3I Atlas in late 2023 and early 2024. Its NIR spec instrument captured high-resolution spectra, and the results were immediately striking to anyone familiar with comet chemistry. The carbon dioxide to water ratio was profoundly skewed. While typical solar system comets might show roughly equal amounts of CO2 and water, or perhaps favour water by a factor of 2 or 3, 3I Atlas revealed a staggering dominance of carbon dioxide by a factor of more than 15 to 1. In some analyses, it was 15.5 parts CO2 for every 1 part water. This isn't just unusual, it fundamentally describes a different class of object. Carbon dioxide ice is significantly more volatile than water ice sublimating at much lower temperatures. In the frigid expanse of interstellar space or the outer reaches of a nascent solar system, where temperatures hover just tens of degrees above absolute zero, both water and CO2 would be locked solid. However, as a comet embarks on its journey towards a star, it heats up. The CO2 begins outgassing first at greater distances from the star where water ice remains stable. Over countless orbits, a typical solar system comet gradually depletes its CO2, becoming progressively richer in water. 3I Atlas's overwhelming CO2 dominance therefore presents two compelling possibilities. Either it has experienced very few close encounters with any star, or it originated in an environment exceptionally rich in carbon dioxide relative to water. The latter suggests a distinct chemical composition in its birth cloud, or perhaps a different formation process entirely. Further data from Spherex, another space-based observatory focused on all-sky spectroscopy, reinforced these findings. Its spectrophotometric data confirmed strong absorption features consistent with water ice, but crucially also validated the extensive carbon dioxide coma first detected by JWST. This CO2 was found to be spread out over immense distances, far exceeding the visible coma seen in optical images. This paints a picture of an object that is vigorously outgassing carbon dioxide, yet paradoxically exhibiting relatively subdued visible activity. It's as if the primary chemical reactions are occurring in the infrared spectrum wavelengths, invisible to the human eye, making the object appear optically quieter than its true dynamic state. Then the mystery deepened with polarimetry, a technique that measures how light is polarized, specifically how the electric field of light waves oscillates in preferred directions rather than randomly. When sunlight scatters off particles within a comet's coma, it becomes polarized. The precise degree and orientation of this polarization offer invaluable insights into the size, shape, and composition of these scattering particles. Every comet and asteroid we've ever studied exhibits a characteristic polarization curve. Typically at small phase angles, when we look nearly back towards the Sun, the polarization is slightly negative. As the phase angle increases, it crosses zero, becomes positive peaks, and then declines. A research team led by Gray published their polarimetric observations of 3I Atlas on the ARSYS preprint server, and their findings were truly unlike anything seen before. The negative polarization branch, that initial dip below zero at small phase angles, plunged to an astonishing 3.5%. Most comets and asteroids hover around 1% to 2%. Even more remarkably, the inversion angle where the polarization shifts from negative to positive was measured at around 105 degrees. This too is unprecedented. Typical cometary inversion angles range from 10 to 20 degrees, while asteroids might reach 30 degrees. 3I Atlas is not just at the boundary. it appears to be entirely outside the range of known natural celestial bodies. This unprecedented polarization suggests the dust grains in 3I Atlas's Comet possess highly unusual properties, perhaps ultrafine grains, incredibly complex internal structures, or even exotic non-terrestrial compositions. What do these profound polarimetric oddities tell us about the dust grains themselves? The particles scattering sunlight in 3I Atlas's Comet must possess highly unusual characteristics in terms of their size, shape, and internal structure. Ultrafine grains significantly smaller than typical cometary dust could potentially account for the extreme polarization. Alternatively, grains with highly complex internal structures, perhaps layered particles or fractal aggregates of different materials, might produce such behavior. Some researchers have ventured to suggest exotic compositions, minerals, or organic compounds rarely, if ever, observed in solar system comets. Others propose unusual surface roughness, or paradoxically extreme smoothness as potential explanations. However, another compelling idea is gaining traction, one rooted in the immense timescales of interstellar travel, the effects of sustained cosmic ray processing. Interstellar space is far from empty. It is permeated by high-energy galactic cosmic rays. Protons and heavier nuclei accelerated to near light speed by supernovae and other cataclysmic events. These potent particles relentlessly bombard any object drifting through the galaxy, penetrating its surface, fracturing chemical bonds and instigating new molecules through radiation chemistry. A recent paper by Maggiolo Dewey and collaborators elegantly explored how galactic cosmic ray processing might alter an interstellar comet. Their model specifically examined the irradiation of an icy surface, rich in carbon monoxide, a molecule known to be abundant in molecular clouds, and by extension likely in interstellar comets. Over millions of years, cosmic rays could convert carbon monoxide into carbon dioxide via oxidation reactions. Simultaneously, they would synthesize complex organic molecules, colloquially known as Tholin's viscous tar-like compounds, and other carbon-rich materials, effectively creating a processed crust, chemically distinct from the comet's pristine interior. This model makes several testable predictions. You would expect a surface layer perhaps tens of meters thick, significantly enriched in carbon dioxide and these complex organics. Beneath this weathered crust, the original unadulterated composition would persist. Any observed outgassing would therefore be sampling this processed layer, not the core. This theory offers a coherent explanation for 3I Atlas's extreme carbon dioxide dominance and its unusual dust properties, particularly if the ejected grains are coated in or composed of these radiation-processed organics. It suggests that what we observe might not represent 3I Atlas's true bulk composition, but rather a weathered, chemically altered shell concealing a very different object beneath. The implications are profound. If 3I Atlas's outer layers have been fundamentally transformed by cosmic ray processing, then inferring its origin and formation conditions from its current composition becomes exceptionally complex. It would require intricate modelling to account for these modifications, working backward from the observed chemistry to its original state. While theoretically possible, this demands detailed assumptions about the object's interstellar journey, the local cosmic ray flux it encountered, and the efficiency of radiation penetration. Many researchers find this cosmic ray processing model highly compelling. It offers a naturalistic explanation for a multitude of otherwise puzzling observations, and generates testable predictions about what we might find if we could, for instance, drill through its crust. Others remain cautious, noting the uncertainties in modelling such long-term radiation effects, and arguing that less exotic scenarios might still explain the data with sufficient effort. Yet this chemical weirdness inextricably links back to the symmetry mystery and the acceleration paradox. If 3I Atlas possesses such a processed crust, and if outgassing emanates primarily from that crust, rather than a uniform core, then its outgassing properties might diverge significantly from a normal comet. Perhaps volatiles are released in a manner that creates more symmetric distributions. Or more intriguingly, perhaps this crust conceals an underlying internal structure, or energy source that remains hidden from our direct observation. The alternative interpretation, the one that persistently resurfaces in scientific whispers, is that this unusual composition is not a product of natural processing at all. If one were to engineer an interstellar probe to masquerade as a comet, an icy exterior would be a logical choice. However, one might not meticulously replicate a natural cometary composition, opting instead for convenient volatiles that provide the necessary properties. The CO2 dominance, the bizarre dust, the polarization anomalies. Perhaps these are not the scars of a billion-year journey through a radiated void, but rather engineering signatures, subtle traces of a construction process that deviates from natural proportions. To be clear, the natural explanation, the cosmic ray processing model, remains a strong contender. It can plausibly account for the compositional data without invoking alien technology. But equally, the compositional data does not definitively rule out an artificial origin. It places 3I Atlas in a frustrating scientific middle ground, where interpretation swings depending on our fundamental assumptions about the object's true nature. To break this frustrating scientific deadlock, we desperately need more data, and crucially different types of data. Observations capable of resolving the inherent ambiguity between natural and artificial scenarios. Fortunately, as 3I Atlas continues its cosmic journey, new opportunities are emerging. Its precise orbit, its interaction with the relentless solar wind, and the evolving structure of its coma and tail when viewed from diverse angles. All these offer avenues to peel back further layers of the mystery. This leads us to the dynamic intricacies of 3I Atlas's motion, and the faint yet tantalizing possibility that human-built spacecraft might someday intercept it to unlock its true nature. Every celestial orbit tells a story. Interstellar orbits recount sagas of the galaxy itself. When an object originates from beyond our solar system possessing sufficient velocity to evade the sun's gravitational capture, it traces a hyperbolic trajectory. It plunges in slingshots around our star and then hurtles back into the cosmic abyss, never to return. To date, we have definitively confirmed only a handful of such interstellar wanderers: Oumuamua in 2017, Comet Borisov in 2019, and now 3I Atlas, designated 3I Atlas, the third such object. NASA's meticulous trajectory data reveals that 3I Atlas reached perihelion, its closest approach to the Sun, at approximately 0.7 astronomical units AU. To put that in perspective, 1 AU is the distance from Earth to the Sun, so 0.7 AU is roughly the orbit of Mars, well within Earth's path, though not dangerously close to the Sun itself. Its closest approach to Earth occurred at about 0.48 AU, or roughly 72 million kilometers. While not close in absolute terms, this distance proves sufficient for high-quality spectroscopy, polarimetry, and precise tracking of subtle shifts in brightness and position. The hyperbolic nature of 3I Atlas's orbit means it is moving exceptionally fast. Unlike objects on bound orbits that slow down as they climb away from the Sun, interstellar objects arrive with excess velocity, already exceeding escape speed, and maintain that momentum throughout their solar system passage. 3I Atlas currently zips past the Sun at several kilometers per second. It's a transient visitor, and our window for study is inherently limited. Intriguingly, before it manifested that strange symmetric structure, and before its tail mysteriously vanished in early November 3rd, Atlas behaved more like a conventional comet. Ground-based observations from the Tidy Observatory in the Canary Islands in late October captured images showing a distinct sunward carbon dioxide plume. While most cometary jets typically point away from the Sun, propelled by sublimation on the sunlit side, 3I Atlas displayed a jet stretching approximately 20,000 kilometers towards the Sun. Sunward jets are unusual but can occur, often explained by unique topography on the nucleus, a cliff face or crater wall focusing outgassing in that direction. The Tidy observations then suggested localized activity with specific regions on 3I Atlas's surface furiously expelling CO2 in concentrated streams rather than uniformly. This pattern aligns perfectly with standard comet models. Uniformity is not expected. The nucleus rotates, solar heating varies, surface composition differs. Jets are normal. What isn't normal is the subsequent evolution. If active jets were producing visible plumes in late October, the expectation driven by increased solar heating would be for activity to continue, or even intensify as the comet neared the Sun through November and December. Instead, the tail vanished. Amateur observers documented a complex sequence of changes. Plumes would briefly appear then fade. A fleeting anti-tail, an optical illusion created when viewing a dust sheet edge-on appearing to point towards the Sun, was also reported. Then, around the time of the November 10th post-conjunction observations, the entire tail structure seemed to dim dramatically, if not disappear entirely. By that pivotal date when the symmetric plasma star images emerged, the tail was effectively gone, replaced by that enigmatic glowing sphere. Some insist the tail still persists, merely very faint, perhaps overwhelmed by the brilliantly symmetric coma. Others argue it's a genuine shutdown of cometary activity, at least in the visible wavelengths. The infrared observations, however, indicating ongoing carbon dioxide outgassing, complicate this binary view. Perhaps the object is indeed still actively outgassing, but the gas and dust distributions have radically reorganized into something far more symmetric. Or perhaps dust production has plummeted while gas continues, rendering any faint tail imperceptible against the dazzling core. The non-gravitational acceleration meticulously measured by Avi Loeb from the precise trajectory data adds another critical piece to this perplexing puzzle. Analyses, including those diligently compiled by citizen scientists on Reddit, poring over JPL Horizon's ephemeris data, reveal a remarkably clean acceleration vector. It does not wander randomly as one might expect from various jets, firing erratically as a nucleus rotates. Instead, it maintains a steady, consistent direction over time. The in-plane thrust component suggests this acceleration occurs primarily within the orbital plane, a slightly unusual but not impossible characteristic for conventional cometary outgassing. By carefully plotting this trajectory, accounting for the measured acceleration, scientists can extrapolate 3I Atlas's journey both backward and forward. The inbound path hints at a specific general direction of origin within our galaxy, though pinpointing a precise source star system remains an insurmountable task given the immense timescales and complex galactic dynamics involved. The outbound trajectory shows 3I Atlas destined to depart our solar system, resuming its solitary drift through interstellar space for millions of years, unless it happens upon another star system. This is where the tantalizing speculation about spacecraft observation opportunities truly ignites. 3I Atlas is currently traversing the inner solar system, and a myriad of space assets are already out there. While missions like YES's JUICE, en route to Jupiter, are not ideally positioned for a close flyby, they might still observe 3I Atlas from a distance, or even sample its ion tail if orbital mechanics align. Other Earth-orbiting satellites or deeper space probes could potentially contribute observations if appropriately tasked. The ultimate prize, of course, would be in situ measurements flying a spacecraft directly through 3I Atlas's coma, or tail collecting gas and dust samples, analysing its plasma environment, and searching for magnetic fields or electrical charge distributions. This direct approach has revolutionised our understanding of comets in the past. The Rosetta mission, for instance, spent 2 years orbiting Comet 67P Churyumov-Gerasimenko, providing unprecedented insights. A similar mission to 3I Atlas would answer countless questions. However, mounting such a mission on short notice is regrettably an impossibility. Spacecraft require years, often decades, for design, construction and launch. Trajectories must be calculated with exquisite precision, and instruments carefully selected and tested. By the time a probe could be readied, 3I Atlas would be long gone too distant and too faint to study effectively. The window for in situ exploration for this object is closing rapidly. Nevertheless, indirect methods exist to probe 3I Atlas's environment. The solar wind, that constant supersonic stream of charged particles flowing from the Sun, interacts with cometary comas in predictable ways. When this wind encounters neutral gas in a coma, charge exchange reactions occur, ionizing the cometary molecules. These newly formed ions are then swept away by the solar wind's embedded magnetic field, forming the characteristic ion tail. This interaction region can also create a magnetic pileup, where the interplanetary magnetic field drapes around the cometary obstacle. If 3I Atlas possesses an unusually dense coma or generates peculiar plasma conditions, we might detect unexpected magnetic structures in solar wind data downstream from its position. Satellites designed to monitor the solar wind for space weather forecasting, missions like ACE-DSCOVA or the Parker Solar Probe, could, if ideally positioned, potentially detect 3I Atlas's subtle influence on the solar wind flow, even without directly observing the comet itself. Such a detection would provide invaluable indirect information about the coma's density and extent, helping to refine models of its outgassing rate and composition. The tail dynamics, or rather the conspicuous absence thereof, remains one of the most perplexing aspects of the entire 3I Atlas mystery. Cometary tails are usually straightforward. Dust particles are pushed by solar radiation pressure, forming a curved tail along the orbital path, while ions are swept away by the solar wind, creating a straight tail pointing directly away from the Sun. Both processes are meticulously understood, extensively modelled and consistently observed across hundreds of comets. Why 3I Atlas would deviate so dramatically, why its tail would effectively vanish precisely when it should be most prominent, defies obvious explanation. Unless, of course, the tail didn't vanish, but rather reorganised. If the dust and gas distributions somehow coalesced into a different, more spherical, more symmetric geometry, if outgassing became uniformly distributed across its surface, or if its rotation rate drastically increased, or if some internal process altered the way volatiles were released, then a symmetric halo might indeed form instead of a directional tail. This would still be profoundly strange, demanding a novel explanation, but it would remain a natural process, not necessarily indicative of anything artificial. The most unsettling alternative, a notion that subtly persists in the minds of many astronomers, whether openly admitted or not, is that the tail vanished because its propulsion mechanism changed. If 3I Atlas were indeed an artificial construct, an interstellar probe utilizing some advanced drive system, one might expect to see varying exhaust signatures during different phases of its mission. Perhaps during its long, silent interstellar approach, the drive was dormant, allowing 3I Atlas to coast perfectly, mimicking a natural comet. Then upon reaching the inner solar system, the drive activated, generating thrust without the messy exhaust plumes associated with chemical rockets or conventional outgassing. The symmetric glow we observed could in this scenario be the very signature of an active propulsion system, a controlled plasma field or directed energy emission free from the inherent chaos of natural sublimation. This line of thinking, I readily acknowledge, veers sharply into the realm of science fiction. But the accumulating observational data defying conventional explanations compels scientists to consider even these highly speculative possibilities, if only to systematically rule them out. The scientific method demands that we consider all hypotheses, no matter how unlikely, and then rigorously use evidence to eliminate them until only the most fitting explanation remains. Right now, both natural and artificial scenarios remain on the table, neither definitively ruled out by the current data. This persistent ambiguity fuels both rigorous scientific inquiry and rampant online speculation in equal measure. Let's circle back to one of the most compelling natural explanations: rapid rotation. A specific, extremely high rotation rate could indeed make an outgassing comet appear symmetric. If the nucleus spins fast enough, the jets of gas and dust observed over a typical 30-minute exposure would blur into a uniform symmetric halo. The mathematics suggest rotation periods measured in mere minutes or even faster. For a nucleus several kilometers across, this translates to surface velocities approaching hundreds of meters per second, a speed perilously close to the centrifugal limits of what an icy body can withstand before fragmenting. While some short-period comets, through decades or centuries of numerous solar passes can be spun up by outgassing torque's 3i Atlas is a singular interstellar visitor. It hasn't had the luxury of orbital evolution to naturally achieve such extreme spin rates. If it rotates fast enough to create the observed symmetry, that rotation must have been intrinsic from its inception, imparted during its formation, or through some unknown cosmic encounter. The rapid rotation model appeals because it's entirely natural, requiring no exotic physics. It postulates that the observed symmetry is an illusion born from temporal averaging. Differences in observed symmetry levels could then be explained by varying exposure times or rotational phases. It fits within conventional astrophysics. However, direct measurements of 3i Atlas's spin remain elusive. Light curve observations which detect brightness variations to infer rotation periods have yielded ambiguous results. Some report periodic variations suggesting several-hour rotations. Others see no clear periodicity at all. The very lack of a strong, obvious rotation signal for such a bright comet is itself peculiar. One would expect surface features and active regions to create detectable brightness fluctuations. Then there's Avi Loeb's alternative framework, which continues to generate both intense interest and significant controversy. Loeb's reasoning is explicit. He analyzes the non-gravitational acceleration data, calculates the momentum budget to determine the required mass ejection and velocity, and then contrasts this with the images showing no corresponding debris cloud or tail. His conclusion: conventional outgassing simply cannot explain the acceleration, meaning something else must be providing thrust. What else could provide thrust in the realm of natural phenomena? Options quickly dwindle. Outgassing is virtually the only known mechanism for cometary acceleration. Radiation pressure from sunlight is negligible for a large nucleus. Magnetic interactions with the solar wind are too weak. Gravitational perturbations are accounted for in models. If outgassing is ruled out and no other natural explanation fits, the scientific gaze inevitably turns to the possibility of artificial engineered propulsion. Loeb frames this in probabilistic Bayesian terms. He suggests that while the initial probability of an artificial origin before the November observations might have been exceedingly low, perhaps 1 in 100,000 or less, each accumulating anomaly shifts that probability. The strange composition, the acceleration without a visible tail, the perfect symmetry. Each piece of evidence, he argues, incrementally increases the likelihood of an artificial origin. Online communities have eagerly adopted this Bayesian framework with amateur analyses, sometimes concluding probabilities as high as 80% for an artificial origin. However, these often rely on assumptions considered overly generous by many within the scientific establishment. Critics push back, asserting that natural explanations have not been exhausted, that we are prone to pattern matching with incomplete data, and that astronomical history is replete with anomalies that once studied closer revealed mundane origins. The engine hypothesis has become entrenched, though the precise nature of such an engine remains entirely speculative. Chemical rockets are immediately dismissed due to the obvious exhaust plumes and mass loss issues. Nuclear propulsion, whether fission or fusion, might produce less visible exhaust, but would generate detectable signatures in other wavelengths, such as gamma rays or neutrons, which have not been observed. Electric propulsion, like ion drives, is highly efficient, but typically generates very low thrust, likely insufficient to explain 3i Atlas's observed acceleration for a massive object. This leaves us with far more exotic possibilities. Solar sails utilizing sunlight radiation pressure could work in principle, but 3i Atlas exhibits neither the expected acceleration profile nor any evidence of the vast reflective surfaces required. Laser sails propelled by directed energy from an external source face, similar problems compounded by the unanswered question of the laser's origin. Hypothetical propulsion systems based on unknown physics, warp drives, reactionless thrusters or space-time manipulation, are fascinating for speculation but fundamentally untestable with current observations. If one were to take the engine hypothesis seriously, it implies a system capable of producing thrust with minimal visible exhaust, efficient enough to accelerate a substantial object and generating a symmetric plasma signature that could be mistaken for a natural coma. This is a highly specific set of requirements, and no known human technology perfectly fits the bill. Some researchers muse that the symmetric glow could be indicative of a magnetic confinement system, carefully bottling and directing plasma exhaust. Others suggest it might be a waste heat signature from an onboard power system, radiating uniformly. The fundamental challenge with all these imaginative ideas is their unfalsifiability with our present data. One can conjure an artificial propulsion system that produces the observed signatures, but one cannot prove its existence. And the natural explanations, though stretched by the anomalous observations, cannot be entirely ruled out either. Perhaps there are subtle complexities in cometary physics we don't yet grasp, ways in which outgassing under extreme unusual conditions can produce symmetric distributions and acceleration without obvious tails. Perhaps our viewing geometry is still playing tricks on us, or multiple natural effects are conspiring to make a natural object masquerade as something artificial. Crucially robust counter-arguments to the engine hypothesis exist within the peer-reviewed scientific literature. A notable paper by Newitt and colleagues, for instance, employed sophisticated thermophysical modelling, combined with Monte Carlo simulations to explore whether conventional volatile outgassing could under specific conditions reproduce 3I Atlas's observed behaviour. Their model incorporated realistic surface temperature distributions, depth-dependent compositions jets driven by subsurface pressure buildup and the chaotic dynamics of rotating irregular nuclei. When carefully tuned with plausible parameters, they demonstrated that carbon monoxide and carbon dioxide outgassing from localized active regions could indeed generate acceleration profiles similar to those measured all without invoking exotic physics. This is a vital point. It illustrates that the natural explanation space for cometary behavior is not yet fully exhausted. With enough model complexity and adjustable parameters, it becomes possible to fit the observational data using conventional cometary physics. The critical challenge then becomes distinguishing whether one is truly fitting a signal or merely fitting the noise, whether the added complexity is justified by independent evidence, or if the model is simply being tuned to match a single peculiar data set. Newitt's work affirms the viability of a natural explanation, though it stops short of proving it is what's actually happening with 3I Atlas. It simply shows it's within the realm of possibility. Beyond the immediate scientific debate, the philosophical implications of the engine hypothesis are colossal. If 3I Atlas were confirmed to be artificial, it would represent humanity's first unambiguous detection of extraterrestrial technology, the irrefutable proof that intelligent life exists elsewhere and has mastered interstellar travel. This would be a civilization-altering discovery, immediately raising profound questions about intent. Is 3I Atlas a probe, a derelict, an accidental visitor? Is it observing us or simply passing through? Does it pose any risk? Traditionally, SETI, the search for extraterrestrial intelligence, has primarily focused on radio signals listening for deliberate transmissions. The concept that alien technology might reveal itself through anomalous motion of interstellar objects fundamentally shifts this search strategy. Instead of passively listening for messages, we would actively seek out objects behaving oddly, scrutinizing trajectories that defy gravitational models, searching for artifacts silently drifting across the galaxy. Both Oumuamua and now 3I Atlas have ignited serious discussions about how to systematically search for such objects and what rigorous criteria would be sufficient to claim an artificial origin. Some researchers have proposed the term starshot detection for this approach, drawing inspiration from Breakthrough Starshot, a project aiming to send lightweight laser-propelled probes to nearby stars. If humanity conceives of such missions, it stands to reason other civilizations might have done so already, perhaps millions of years ago, by civilizations that may not even exist anymore, their probes still executing ancient programs. The statistics here are crucial. Based on current detection rates and the sensitivity limits of our surveys, astronomers estimate that several interstellar objects pass within a few astronomical units of the Sun every year. Most are too small or too faint to detect. We only spot the larger ones, and then only if they pass relatively close to Earth or develop visible cometary activity. If even a tiny fraction of these interstellar objects, perhaps 1 in 1,000 or 1 in 10,000, are artificial, then we might expect to detect one every few decades or centuries. Two potentially anomalous detections, Oumuamua and possibly 3I Atlas, in less than a decade of the modern surveys is either a remarkable statistical coincidence or a tantalizing hint that artificial objects might be far more common than our current paradigms suggest, prompting us to re-evaluate the Fermi paradox. But we cannot simply declare victory for the alien hypothesis based on ambiguous data or frustration with natural models. Science demands rigor, the systematic ruling out of alternatives and independent confirmation. What we critically need are observations that would yield dramatically different results under natural versus artificial scenarios, measurements capable of breaking this frustrating degeneracy. This includes definitive imaging that either confirms or rules out traditional tail structures, spectroscopy sensitive enough to detect truly exotic chemical signatures, polarimetry across a broader range of wavelengths and phase angles, and even radio observations specifically searching for any emissions indicative of electronics or power systems. Recognizing the significance of 3I Atlas, the International Asteroid Warning Network IAWN, a collaborative effort of observatories and space agencies focused on near-Earth object monitoring, has prioritized 3I Atlas for continuous observation through the end of 2023 and well into 2024. Multiple telescopes are actively tracking it, collecting photometry and astrometry to build a comprehensive dataset. Advanced polarimetric campaigns are underway with facilities like the Very Large Telescope and Nordic Optical Telescope, dedicating time to measure 3I Atlas's polarization with unprecedented detail. These ongoing observations will either corroborate the unusual properties reported earlier or ultimately reveal them to be artifacts of limited early data. What we collectively watch for in the coming weeks and months is change. If 3I Atlas is a natural object, its behaviour should evolve predictably as it recedes from the Sun. Activity should diminish as solar heating wanes. Any symmetric structure should eventually break down as outgassing weakens and becomes more irregular. The bright coma should fade, potentially revealing more about the underlying nucleus. If, however, 3I Atlas is artificial, its behaviour might diverge significantly. The symmetric structure could persist, its acceleration might continue unchanged, or it could vary in ways that show no correlation with solar distance. New unexpected features might even appear as onboard systems activate or deactivate. Every night, somewhere on Earth or in orbit, someone is pointing a telescope at 3I Atlas, capturing photons that have travelled across the solar system from this enigmatic object. These photons carry an immense amount of information encoded in their wavelengths, polarizations and arrival times. Our task as scientists and observers is to painstakingly decode that information, translating it into measurement images and spectra, striving to construct a coherent picture of what we are truly looking at. Sometimes that picture resolves into something familiar and reassuring. Sometimes it deepens into an even greater mystery. And sometimes, very rarely, it hints at something we had never even dared to imagine possible. 3I Atlas currently resides in that intensely uncertain space, neither unequivocally natural nor demonstrably artificial, profoundly challenging our assumptions and forcing us to question how deeply we truly understand the universe we inhabit and our place within it.